like.
Oh, but when you get to that point, then I would save it without default. Then I'd be like, okay.
Shameless save scumming. Yeah, that's what it's called.
good? Yeah? Hello, everyone.
Good evening.
Welcome to Privacy Lab. Who here has been to a Privacy Lab before? Great. Privacy Lab is a monthly event co-hosted by EFF and Mozilla to talk about all sorts of different privacy things, sort of every range of topics. This is a pretty cool one here at ICSI. We're going to talk about mobile privacy and how to determine what your apps are doing. Next month, we're going to be talking about student privacy, and then we're going to be talking about data protection and how corporations deal with data. So if you want to go to future privacy labs, make sure that you are on our email list. You may have just been subscribed to our email list because I did a big sweep of old signups recently. And keep an eye on the wiki. There'll be future Eventbrites. We don't have a location for next month yet, but it will be coming shortly to your inboxes. If you have ideas for future privacy labs, or you maybe work at a company, or you're an academic who has a space that can host a future one, come talk to me afterwards, because we're always looking for new topics or suggestions about what to be talking about. Anyway, today we have 4 wonderful speakers. We have David Choffnes. I probably butchered your last name.
No, you got it perfect.
Great. Who will be talking about Recon. We have Narseo Vallina-Rodriguez, who will be talking about Haystack. We have Primal, who will be talking about some user studies on mobile privacy. And we have Kashmir Hill, who will be talking about the Waze app and this recent hack that it was victim to. Each speaker is going to talk for about 10 to 15 minutes, and then afterwards there'll be time for just 2 questions because we want to make sure we get to the next speakers. If you have questions that you didn't get a chance to ask, don't worry. All the speakers are still going to be here when we finish talking. You can just come up to them and talk to them personally. In fact, I encourage everyone to sort of just, form small groups and talk about whatever they find interesting from the Privacy Lab. At some point around 8, we're going to get kicked out. It's sort of up to the ICSI people when that is. I'm going to have to leave before then, so I'm going to leave it up to their discretion. Yeah, you should feel free to talk after all the speakers are done. So if anyone is watching on the web stream and has questions, I think there is a chat box on the YouTube link, and you can ask questions in there, and I'll try to relay them to the speakers so you can hear them. Otherwise, yeah, there'll be lots of opportunities to talk. So first, David is going to talk about Recon.
All right. Okay. Thanks for having me here. Today I'm going to talk about a system we've been working on called Recon. So the motivation for this is pretty straightforward. We love our mobile devices. Pretty much, I assume, who here does not have a smartphone? Anybody? Okay, so there's 2 people in the room for those on the web stream. A very small minority of people who are very proud not to have smartphones, but most of us do. And we carry them in our pockets and purses, and we love them because they have all kinds of interesting sensors. They count our steps, and we can track our health, and they're always connected to the internet. But then there's all of this other stuff that they are getting access to. We enter our usernames, our passwords, our email address, all kinds of information, and there's other things that they store and track us with. So some key questions that we wanted to answer as part of this work is what personal information is being shared, who gets this personal information, and given that, not surprisingly, you're going to learn a lot of information about us is being transmitted to other parties, what can average users do about it? How do we fix these issues? So we started, before designing anything, with a study to understand exactly what's happening. What are our apps learning about us? And the way we did this is with controlled experiments. These were manual experiments, so my student, bless her soul, spent many weeks of her life she won't get back, actually manually interacting with the top 100 apps for each OS, and by that I mean iOS, Android, and Windows Phone. And we seeded these devices with very conspicuous PII, and for those who don't know, PII is personally identifiable information, basically anything you would probably consider private or that could be used to identify you. So we seeded them, and in this way, if they're transmitted over the network, we could easily search for them. It's essentially doing a text search on network traffic because this text should never appear naturally. So we did this, and we found actually the reason why we did these manual experiments. If you look at the comparison with what is sent over the network with manual tests versus, say, automated interactions, we found manual tests found a lot more information. And it's just that automated tests don't really know how to interact with an app. Usually they don't even know how to log in, which means they can't do anything. Okay, so what did we find? What I have here is a graph of the fraction of apps leaking each type of information, and each type here is on the x-axis, just grouped into categories like user identifiers, contact information, location, credentials, and device identifiers. And so each bar represents a different OS. Blue is iOS, that's the App Store. Google Play is red, and orange is the Windows Phone Store. So what immediately stands out, the most common forms of tracking are what we would call sort of run-of-the-mill tracking, things that if you're all paying attention, you'd expect to find. Device identifiers are leaked extensively, so they're able to uniquely identify you across multiple sessions. Your location is being leaked, so I'm sure many of you have noticed when you use an app, the GPS icon comes up, even if you're not actually needing to do anything location-based. So basic tracking is common, and that's unfortunate, but it wasn't terribly surprising. What was surprising to us is that there was a significant fraction of very personal information being sent over the network. And I should remind you, or I should note, all of this was sent in plain text. None of this was encrypted. And that includes, in several cases, passwords being sent over the network. And I'll get back to that later. Okay, so this is what we found. PII leakage is basically pervasive. So we have a pretty big problem to solve here. Okay, so the question is, now that we found this, how do we go about doing it in a more automated way and provide not only a way to detect that this information is leaking, but also control it? So one approach that's been proposed in other research projects is build it into the OS. So do something like information flow analysis, which basically tracks how personal information data that's stored on your phone is basically how it flows through various apps and then out through a network interface and flags it. So these are great in terms of not missing information leaks, but unfortunately they have very high false positive rates, and also if you run these types of solutions on your phone, it slows to a crawl. These aren't things that average users are going to use. Another approach you might want to think about is what we did, which is look at the network traffic. And one of the advantages here is now we don't have to hack an OS. We don't have to rely on any OS vendor to support it. We also don't have to rely on an app store. So this is essentially completely portable because all of these devices boast having internet connectivity. So all we need to do is get access to network traffic. And from the study we did just on the previous slide, it's actually pretty easy to detect information from network traffic if you know what to look for. So like I said, it was really just doing text-based searches. So one of the key problems, though, is if we're giving this to average users, or say hundreds or thousands of them, we don't know what their information is. And some of these things, users don't even know what that information is. So how many here know what your IMEI is? Wow. Okay, 3, maybe 4 people in the room. More people know their IMEI than those who don't have smartphones. This is very great. I love this crowd. Okay, so for the rest of us, clearly this isn't something you're going to know off the top of your head and necessarily be able to provide to a system to search for you on your behalf. So what Recon does is it addresses this problem of automatically identifying these leaks. And the hypothesis we have is that when your information leaks over the network, it's going to have some kind of identifying characteristics in the network traffic that they use to leak it. So for example, if you've ever looked at HTTP traffic and you've seen essentially key value pairs either in get or post parameters, you'll see something like user equals recon. And so you might reasonably infer that, oh, well, if I see user equals, maybe that means that my username is being sent out, and so this is something I should flag as my information being sent out. And so we actually evaluated, is it that simple? And the answer was, well, it's right some of the time, but it also can lead to really high false positives and false negatives. So essentially, you're going to have a noisy approach. If I were to give you a piece of software that did this, and it showed you what was leaked, you'd find a whole bunch of cases that make no sense. And we want to try to minimize that as much as possible. So instead, what we do is we learn the structure of these leaks based on examples. More specifically, we're building machine learning classifiers that allow us to reliably detect leaks, distinguish cases where it's actually a username being leaked from those that aren't. And the nice thing is now, no user has to tell us in advance anything about their personal information. And if formats change over time, because we use machine learning, we can adapt the system. It's not pinned to any hard-coded format. Okay. So now that I've sort of given you the setup for what we're doing, I want to tell you sort of at a high level what Recon consists of. So first, as I mentioned, we use machine learning to reveal information leaks from mobile devices. And what I've shown here on the right-hand side at the bottom is we essentially have two phases. We do some controlled experiments where we train an initial classifier. And then what you see in the bottom part is a very similar thing, except now we have users in the loop. So we are doing predictions based on a classifier we trained in the lab, but users can go in and tell us if we're right or wrong. And based on that data, we can retrain the classifier to make it more accurate going forward. So that's the machine learning component. Now, that only works if you have access to network traffic. And so in general, it's not necessarily obvious how you would go about getting access to that traffic. What we use is a bit of a hack. So instead of actually hacking the OS or rooting a phone, we wanted a way to get access to network traffic from any phone without any special privileges. And the way we do this is using VPNs. So pretty much all devices support VPNs. The main reason is enterprise customers need this. And instead of using it to access a private network, we just use it as a proxy. So regardless of whether the user is on Wi-Fi or cell, they can tunnel their traffic to a server, that a system we call Metal, which is something Recon is built on top of, and then that traffic goes through a metal box. So the idea is it's a little play on metal box for those who. Anyway, so what you see is the Recon runs inside the metal box. So it's something that we can then use to analyze and potentially modify the user's traffic based on their preferences. So we use these software metal boxes to get access to network traffic, and then users can tell us what they want using a web-based UI, which basically makes it run on all platforms. So just a brief overview of some of the things we have today. You could view your detected leaks. So on the right-hand side is what that web UI looks like. So you see various types, categories of information we found being leaked, a little description of why you should care about a specific kind. And then if we've seen it leaked, there'll be an example of it. Tells you who it's sent to. And then you see that thing where it says correct. Users can actually label that for us. They can tell us, is this correct or is it incorrect? And then if it's incorrect, well, we'll learn from that. And we won't show you leaks like that again. If it's correct, well, that will reinforce our classifier. So that's viewing leaks. There's also, that's what I was supposed to show before. So you have also two other options. I'm not sure about this, or this information is not about me. I won't get into that in this short talk. There's also an interface to show location leaks that's a little bit different. So just giving you a list of GPS coordinates is not terribly useful. So instead we figured we'd put it on a map in an interface that we call Where They Know You've Been. So you could basically see all the pins dropped. You can figure out who has collected information about you being at a certain location, and you get a pretty good sense. And very quickly, you see lots of pins dropped all over the place, and you get a sense of just how pervasively your locations are being tracked. And so these are the kinds of interfaces that we'd like to have more instances of, the kind of things that maybe creep people out a little bit, so that they're actually motivated to do something about their privacy. And the last thing is, so far we've painted a very depressing picture of privacy, and the average user might look at that and say, oh, I just want to throw my phone in the garbage, like the two people who don't have smartphones in the room. So we'd like to think that there's a better way, and we wanted to give users control over those leaks. So mind you, because all the traffic is going through our software middle box, we can actually modify it if users want us to. So they could tell us, just block any flow that matches this criteria. I don't want my password to be sent in plain text anymore. So just block traffic. If that means I can't log in, that's fine. Just block it. Don't let it go don't let it go exposed. We're also working on other interfaces that would allow you to randomize the unique tracking IDs, allow you to coarsen locations, and then like other crazy things you might want to do. Like maybe you want to go shopping as if you look like someone in a different demographic than you. Because some of my colleagues' research has shown that companies using algorithmic pricing will show you different prices based on who they think you are. So you could have a way to kind of make yourself look like someone else. Another thing you might want is to hide in a crowd of other users that all look the same, giving a higher level of anonymity than just someone who randomizes identifiers all the time. Okay, so these are some of the things that we can provide with Recon. And this is like the most technical part of the talk before I go back high level. I've talked about using machine learning, but I haven't said much about how we do it. So for any of you who are familiar with machine learning, that itself almost means nothing, because you should be asking the question of what are you using to train your classifier? What is your classifier? How accurate is it? And does it actually make sense? So we've run a lot of tests and analyzed it a bunch of different ways, and there's a paper that you could find about this on the Recon website, so I will not go into those details, but I'll just talk about it at a high level, which is to say we used manual tests. We trained our classifier using tenfold cross-validation, which is sort of a standard way of doing things. When we did that, with the approach we used, we found it had extremely high accuracy. So 99% overall, relatively low false positive and false negative rates. And the accuracy is almost a little too good in the sense that we weren't sure that it was doing the right, could we believe the results? So it worked well for two main reasons. One is that instead of training a classifier based on all network traffic, we train it based on where the traffic is going, under the assumption that the targets of where the traffic is going all use the same format, because there's probably just one API for a given target. The other thing is that we use decision trees. And we did this both because we found they were accurate and because they are interpretable. So I can show you a decision tree where if you follow one of these red paths, it's showing you how you get from a flow containing certain things or not containing certain things to a decision as to whether it's actually leaking information or not. So these kinds of data structures will represent these cases where user equals recon is not sufficient to just look at user. There's a bunch of other things that need to be present to actually flag it as a leak. Okay, so that's all I'm going to talk about for machine learning. And in terms of some of the things we found with our user study, so we currently have just over 300 users, and any of you can sign up as well on the website. They're about half and half, iOS and Android. When we did a small survey with some of the early adopters, vast majority found the system was useful and actually changed their behavior in response to some of the PII leaks that they saw. All told, we found about, just under 26,000 cases of leaks. About a third of them have been confirmed. Often users just don't go in and confirm everything or don't know if something is actually their information, so we still find this to be pretty good. In terms of details, lots of credential leaks. On average, we see more iOS more leaks from iOS devices than Android. We can't claim generality here, but we did control, we normalized based on the populations that we have. So it's not just due to the fact that we have a few more iOS devices. There were a bunch of suspicious leaks. For example, your flashlight app will send data to 12 different tracking companies. And that kind of stuff has probably been, somewhat reported in the news. So some of these weren't terribly interesting, but what we certainly found interesting was all of those passwords being leaked in plain text. So to date, we've identified, I need to update that. I believe it's now 24 apps, 22 apps exposing passwords in plain text and 2 more sending them to third parties over encrypted channels, but should not be going there. Some of these were used by millions, so Match.com is one of the examples. They were nailed for doing this over the web. They fixed it on the web, but they did not fix it on their Android app. So we notified them, they have since fixed it. Hippocrates is an app often used by physicians and medical professionals. Their credentials were exposed in plain text. So we responsibly disclosed all of these. We give companies 3 months to fix the problem before we go public. Most, but not all of them, fix it well before then. And then in some cases like Hippocrates, we also worked with them to give them time to notify their users and try to get everyone to update if they can. Still, only 14 that we've notified to fix the problem. Interesting things that we hear from the developers when we talk to them. So first of all, thank you for responsibly disclosing this. They're very, good to work with. One case was a messaging app that they secured their password, but they were also sending the messages themselves in plain text. And their response was, we do not claim to be a secure messaging app. So that was weird. For one of them, sending passwords in plain text is intentional. Does anyone know why this might be required? No, it's much less nefarious. Think older technology. So feature phones, exactly. Feature phones don't have full-fledged browsers. They have proxies that translate normal web pages into something that can be displayed on the phone. And so to do that, you have to keep everything in plain text. So for those users, one of these services actually needed to keep it in plain text.
Which were the 2 companies that gave you those bottom 2 answers?
That what?
What were the 2 companies that gave you those bottom 2 answers?
They gave me...
The bottom 2, which ones were they?
Oh.
Companies were the bottom.
Neither of them is like at the level of Match and Hippocrates. They are on our website. If you look for the messaging app that has leaked a password, it's them. This one, I forget the name of it off the top of my head. It was a weird service. It's apparently a service that's been around since feature phones were the only phones. So, right. So that's, and there's some, like I just said, that we sort of recently found and is still under responsible disclosure, so we can't talk about those. But, so this was disappointing, but fortunately most of them have responded. There was one, Flickster, never responded to us until they were acquired by Fandango. And then we contacted them again and got a very fast response. So some of this, there was another case that was fun. It was the Windows Phone version of an app, but the developer used a third party to build it, did not have the source code, and that company became unresponsive. So they were unable to fix it because they can't. So you learn a lot of interesting things when you talk with companies about this stuff. I think I've gone mostly over my time, so I'm just going to wrap up quickly. If you want to see reports anonymized in the sense that we just group what we found being leaked for different apps, you can go to the recon.metal.mobi website. We have it separately for apps and also for mobile web browsing, just because those are sort of if you just treat Safari as or Chrome as or Mozilla Firefox as an app, that seems unfair if the websites are doing the damage. So we have web report differently from that. And our code and data from our manual test is also online if anybody wants to play with that. Okay, so to wrap up, clearly there's a need for improved transparency and control over information leaks. Recon addresses this by learning what information is being leaked, using crowdsourcing to extend and improve our accuracy, and then allows users to actually do something to that traffic. So we have an ongoing user study. We've shared our results with the FTC Consumer Privacy Division. I'm told I will never know if they actually use my data because that's how they operate in the dark. And there's actually a documentary film that apparently the final cut of the film is happening this week, and the filmmaker will be shopping it around to festivals soon. So hopefully there'll be something interesting there soon as well. So that's it. I guess hopefully we have time for a couple of questions, and I have to thank the Data Transparency Lab for supporting the work.
All right, maybe 1 or 2 questions. I'll pass this microphone around.
So when you are thinking about the next version of this implementation, are you thinking about a VPN where you ask the user to install a root certificate so you can see the traffic over HTTPS?
Yeah, that's a great question. Basically, the question is related to TLS interception, so we can see the contents of encrypted traffic. So. The answer is yes, but in a different way. So if our system will intercept traffic, we don't want to do it in a shared environment. We would like to produce a version of the system that a user could run, say, in their home network, on hardware they control, in an environment they control, and only do decryption of data in that context. And then the trusted root certificate would be one that they generate using our software. So we want to be very careful about how we do that. We do intercept TLS traffic in our controlled experiments, so we've done a lot of analysis on that as well. But it's a great question. Going forward, increasingly, thanks to Snowden, we will see more TLS traffic. And we have seen that already, so we absolutely have to look at that.
Traffic TLS?
You mean for Recon?
Yeah.
It's not, I mean, it's not personal information.
Does the app make HTTPS requests?
Oh, we don't have an app. It's a web interface, and it's sent over a VPN, so it's already encrypted. Because you have to be running a VPN to access it. But in the future, if we give it to people outside of the VPN, then yes, we would be using TLS.
All right. I'm going to save the rest of the questions for afterwards.
Okay. Sorry.
That's fine. And we'll save.
There he goes. Okay. So I'm Narseo Vallina from ICSI. And first of all, I would like to thank Mozilla and DFF for organizing the Privacy Labs, and also ICSI's admin team, who did a lot of a great job actually setting up everything locally and making all the arrangements. So what I'm going to talk about is basically a system which is somehow similar to Recon with a big difference. Because to some extent what we are doing is collecting the traffic locally, but I will describe all these details later. Somehow the solutions will also complement to some extent if you put them together, and that's something that I hope David and I will discuss in the upcoming weeks. So before getting into details, I also want to acknowledge the great team behind the Haystack app. And those are Abbas from Stony Brook, Recon from Samsara and ICSI, Christian Kreivik from ICSI, Mark Coleman from ICSI, Philippe Bagil, who is just over there, and Vern Paxson from ICSI UC Berkeley as well. So the point that I want to convey in this talk is whether we know everything about what our mobile apps are actually doing with the data that we entrust to them. They request a bunch of permissions, but we don't know where this data is actually flowing. And let's navigate through what a normal privacy-aware user will do when installing an Android app. In that case, I pick up Cut the Rope, which is a quite fun application if you haven't tried it, but if you care about privacy, just reconsider it. And basically, the user may actually check whether the developer is trusted. Google Play tells you that this is a top developer, so it doesn't sound too bad. Then you check the ratings, and you see that they are quite positive. I don't know how many of you actually check for those details when installing an Android app. I guess most of you. Then a user may also want to check the distribution of the permissions, because maybe they are not legitimate. There are services that actually buy installs, and you pay for them and in order to promote your app on Google Play. If you go more in detail, you also check the content of the user reviews, and here you have the first hint. some 2 users actually complain about having a lot of ads on the app. So you may decide not to install the app, or maybe, yeah, it's okay. I'm basically using the app, I like it, and I'm gonna keep going forward. And then, I don't know how many of you actually check for the permissions on your Android apps. Okay, that's a good ratio. And the next question is, do you understand what the permissions imply? Okay. I find it actually hard sometimes even myself. So here we can see that the application is actually requesting which applications you're running, which doesn't seem normal for a game that is supposed to be run by children. And it's also getting the location, but not only the network position location, but also the GPS. So it means that somehow they're trying to track. And the final check, which I would also like to do a survey, is checking the privacy policy. How many of you actually check the privacy policy for any app? Basically, I'm seeing the same people all the time, so it's okay. But if you click on that specific app, you get nothing. So they're basically trying to say that it's in the process of being developed, but this actually happens for most of the mobile applications. So how do we know from Google Pay at the time of installing an app whether the applications are actually managing the data that we entrusted them correctly? And the questions we want to answer is, do they actually leak any of our personal data? The second question is this data going to third-party services, like analytics services, ad networks? And the third one is, do they actually upload the data over secure channels? Do they use TLS? And if they use TLS, do they actually use techniques like certificate binning to prevent middle boxes from intercepting the traffic? We have done a study 2 years ago where we saw that for some mobile carriers in the US, you can find up to 60 additional certificates on the root stores of the phones that they subsidize. So it means that they can easily do TLS interception if they really want to, because they already have access to your root store. So those were some of the motivations behind developing Haystack. And Haystack actually started a few months after David started working with Metal. And we thought that maybe we could perhaps do it in a different way, not just to, basically because we're academics, so we have to do things differently, otherwise we don't publish the papers. So we tried to basically create a tool that is completely user-centric, that runs on the phone, and that, as David properly framed, checks for your traffic in order to identify privacy leaks and also to identify where this data is actually going. But the difference, or one of the advantages of following that approach, is that it can run on user space locally on the phone. So we are not uploading all users' traffic to a shared environment, or to perhaps, as you will perhaps do with ISP traces, we are not actually having access to the metadata of the content. So we can find some balances here. The first one is that by running locally in the phone, we can provide context to the measurements. So we can accurately map flows to applications by looking at information that provides the operating system. So we know exactly that application X talked to seed.com, and we also know exactly that, for instance, the DNS lookup that corresponds to the destination IP address. The second one is that we can also capture real network stimuli and user stimuli. And by making the application available by running on user space on Google Play, we can also increase the diversity of apps that we can study by crowdsourcing the measurements through users. So now I'm going to talk about the technical details of Haystack. And it's going to be perhaps the hardest slide in terms of technical components. So how we intercept the traffic is by using the by using the VPN permission. But we intercept the traffic locally, and we do the proxy locally on the phone. So once we capture the traffic of the applications, we send it to the final destination. Doing that on user space on the phone was actually pretty hard, because you're reading raw packets, but you have to use Java sockets on the other side. So you have to do a flow reassembler between a layer 3 and layer 4, and doing that efficiently was quite challenging. In addition to that, as we're running locally on the phone, users can opt in to do TLS interception. So they can create a root certificate that is created for each one of the devices during installation time. And therefore, they can also see whether their personal information is also leaked over TLS. In addition to that, we're also using that feature to see how applications are using TLS. So what kind of extensions they're using, if they're using countermeasures like certificate pinning to prevent TLS interception and things like that. And then we expose the traffic that we are collecting to another process that is running off path, because if we're doing all the analysis in path, it will affect significantly the performance and the battery life of the phone. So in that case, this is a process which we call the traffic analyzer that combines all the information that we can collect from the operating system. So we know exactly which messages you have on the phone. So we can search if an application is using the same permission to leak that information outside. We are, for instance, collecting the SSID, the MAC address, all these features that you may think that an application may use to somehow track you and also to collect the personal information about you. And we are sending anonymized reports to a server that we control for studies. But we are not sending the whole payload. For instance, we're uploading application X, leak the IMEI without getting the value of the IMEI to server xyz.com over TLS. So we are not collecting any personal information about the users because we have to be ethical. And I think that the research community has made a lot of a serious move in that sense in order to protect the data of the people participating in studies. If you want to know more about the paper, we have it on arXiv, and I invite you to take a look. And this paper contains all the technical details about how Haystack works, and also about the measurements that we are conducting and what we want to do in the future with Haystack. Because this is not only about privacy, but we are somehow envisioning a tool that will allow us to do a wide range of mobile measurements on mobile phones. But Haystack is not only a tool for research. We want to make it available for users. And you can go to Google Play, you can install it. It may not run if you have a Samsung phone, and this is an issue that we have encountering because Samsung modifies the VPN API. So you have to be a partner of Samsung in order to take advantage of that feature. And these are some of the screenshots of the application. We had a talk with the EFF guys in February, and I think Cooper said that the UI was really bad. So we put some effort on improving it, and here you can see, I think the resolution is not very nice, but the application allows you to, for instance, see for a given application which domains are associated with it. So the user can be aware of whether the application is leaking the information to third-party services like analytics services or ad networks.
All you have to do is unlock the actual allow non-set with a direct link.
Pardon?
Unlock the actual, in Samsung you can unlock it to get the direct link. Don't go to the Play Store. You can actually download it.
Yeah, we have it on the, so sometimes it works, sometimes it doesn't. So that's an issue that we had to deal with. We also tell users what kind of personal information that we can collect from the operating system is being leaked by those applications and where this is going. And for instance, we have seen browsers that are used by tens of millions of users leaking the IMEI in plain text. And those browsers are, in theory, used for Chinese users. So Great Firewall of China, track your people easily because you have a unique identifier there. And for instance, some of the interesting privacy leaks that we found are applications leaking which applications you have installed. And that's quite interesting because, for instance, in the case of the 7-Eleven app, you can see that if you have installed applications like Auntie Anne's Pretzels, they will report that you have this application installed. And we can see that as well in a lot of airline applications, reporting if you have, I don't know, airline A application, they will tell that you have airline B application as well installed. So I guess that this is just for some marketing purposes.
So they're not leaking all the applications?
No, they target the specific ones.
Sure.
Yeah. So the UI is not great, and that's something that we really want to improve, and we would like to hear feedback from the community about how we can improve it and make it more usable, and what you would like to have as a feature on Haystack. And now we'll move into what we are doing with the data we are collecting. So as I said, we have to be very careful with the ethical considerations of looking at users' traffic. So for that, we're trying to anonymize as much as we can all the data that we are collecting before uploading it to our servers. And so far, Berkeley's IRB, which is the internal reviewing board, they have considered this study as a non-human subject study because of all the anonymization process that we are following. And we have so far had access to more than 500 users, which allow us to check more than 1,600 apps. And with the data, we are trying to create some sort of catalog of mobile applications. And now we'll move into some sort of real-life demo. And I invite you to check it, which is haystack.mobi/panopticon. Sorry. Cannot I move it? 1 second, sorry about that. Okay. So here in the center, you can see all the third-party services that we have found so far. Those are around 200. And the blue dots are free applications, the green dots are paid apps, and the purple dots are pre-installed apps. So if we filter the top services, the most popular ones, we can find a couple of big players. The first one is Facebook. Facebook is not only allowing applications to integrate your application in their social network, but it's also providing analytics services. The other big player is actually Crashlytics, which is owned by Yahoo, and we have found it in 1 out of 4 apps. So it's actually the analytics service that is being actually used by most of the applications as of today. And then the third one is also owned by Yahoo, and it's Flurry, which is a traditional analytics service. And now let's search, for instance, for an application, Cut the Rope. And you can see the whole network of trackers, and actually that has happened again. Sorry. Yeah. And it tells you all the trackers that are associated with this app. And Cut the Rope is actually linking your data to 16 different third-party services. Some of them are very interesting. You can find game-specific analytics services like game analytics. You can find services that are used to promote apps like Lift Off. So those are the ones that are delivering ads about other apps. So basically you install it, and therefore they increase the number of installs, and they can collect more users. And I invite you to take a look at the Haystack Panopticon, because if you want to take a look at what applications are doing, it's actually quite fun to play with it. And of course, if you want to contribute to the data collection, you can install the app and give us more data points about what the applications are actually doing. So let's go back to the slide. So we look at the distribution of analytic services across apps. And here you can see that around 66% of the apps are using at least one third-party service. And most users are actually caring about how much bandwidth they're wasting on tracking or on ad networks or whatever. And we also plotted it. And here we can see that around 41% of apps waste at least 10% of, or generate at least 10% of their traffic in order to communicate with third-party services, either analytic services or ad networks. And if we aggregate all the applications that are using at least 50% of their volume, you can find that this accounts for 23% of the applications. So it means that a huge fraction of applications is just using the network to communicate with third-party services. And we have some ongoing efforts in the case of, in the topic of improving or providing a better exposure about what applications are doing. And we want to understand what third-party services are actually doing with the data. And this is actually pretty hard to infer, but we are trying our best. And we want to, as I said, improve the usability for average users, not just privacy-aware people like most of the people here. And we want to also enable user actions in order not just to prevent or to anonymize data, but also to perhaps engage in the research efforts that we are conducting. So you can envision users reporting some activity that might be of interest, saying, hey, I found this, take a look at that. And that will provide us a lot of very valuable information to better investigate what those services are actually doing. And we are working on doing something very similar to what Dave is actually doing as well, which is the Haystack Analytics. So we want to create some sort of REST API where you can actually run queries on our database, just to find what kind of analytics services are being used by apps, what kind of protocols they use, the certificates that they are using for TLS, you name it. So whatever we're collecting, we want to make it completely public. And this is it. I invite you to take a look at the app, and if you have any suggestions, recommendations, or what you would like to have on the app, just drop us an email, and we'll be happy to discuss it.
I have a question. What are you, with the role of this, are you guys doing anything in the government space?
In there?
And in the government space with all these different, government applications, infrastructure, et cetera?
We are collecting what users run.
Okay.
So it's completely crowdsourced. If someone running Haystack is having one of those apps, we will be able to infer that. We have actually found on the data prototypes. So for instance, some big players that you may know, they are releasing applications, prototypes, or perhaps beta versions. We have access to all this as well.
With Recon, we've had some people ask us to run it on their behalf to make sure that they weren't leaking things.
One more question, but you should move the...
Yeah. I'm partially that. So
is there any app that would prevent a transmission of your microphone? Maybe like turn your microphone fully off without turning your phone off? Will it block, or can it track voice transmission from your microphone?
Oh, not in that case, because that will require, if I understood correctly, it will require accessing the operating system. So in that case, yeah, those are the cases that they've mentioned before. There are techniques like Tendroid that basically modify the operating system, and they can somehow prevent that kind of leakage. Also, Android now allows you to turn on and off the permissions on runtime. So if you're worried about an application requesting your mic, you just can disable it on the settings.
Right. Okay, so now we have Primal talking about his user state. And yeah, there'll be lots of time for more questions after all the speakers.
Hello everyone, I'm Primal. I'm from UC Berkeley. So this talk is going to be slightly different from what you heard in the last two talks. So it's like, I'm going to talk about the work that we have done, more focusing on the usability side from the user perspective. We do focus on understanding how third-party applications are accessing our sensitive data, but we also emphasize on helping the user to make better privacy decisions. So before delving into any details, there's this notion called contextual integrity, which suggests that privacy is contextual, which means that, which also implies that individual user privacy decisions are mainly driven by the expectations that they have on which applications have access to your sensitive data under a given context. So that raises two different questions. So if a platform wants to protect users' privacy, they have to understand users' expectations under a different context. And then it goes on like, what are the factors that define context? How do an average user differentiate between two different contexts? What are the contexts that third-party applications access to sensitive data? So to understand the last question, to explore understanding how third-party applications behave in the wild, we conducted a field study where we asked users to use an instrumented Android version for a period of 1 week as their primary phone. So we instrumented Android 4.11 to log whenever a third-party application access a sensitive resource, we log them. And along with the permission request, we also log all other contextual information surrounding that permission request, like when the application requests a sensitive resource, what was the status of the Wi-Fi, what was the last known location, what was the status of the screen, what's the app the user was using. And then we also probabilistically took a screenshot whenever we encounter a sensitive permission request. So when users came back to return the phones after the user study, we randomly selected 10 to 15 different screenshots, and then we showed them along with the permission request that triggered the screenshot. The red line is the one where it says this application accessed this data. And then we asked an important question, what would you have done if you had the option to deny or allow that particular permission request in runtime? So we had 36 users using our custom Android version for a period of 1 week as their primary phone. And after the study, we have collected 27 million permission requests and accumulated over 6,000 hours of real visit. There are more surprising facts, more frustrating to hear. Okay. So the first surprising fact was that 75% of the time, users didn't have any clue or any idea that there is an application accessing their sensitive resources, let alone there is an application running. Because 75% of the time, the applications were running invisibly when they access these sensitive resources. So in Android, there are app indicators to answer this specific question, to keep the users informed there is an application accessing a sensitive resource. For an example, the location icon. But what we found out from the study is that the location icon was only visible 0.04% of the time. Because 99% of the time, applications were using network or passive providers, which didn't trigger the location icon on the notification bar. Because Android, in 4.11, Android was showing the location icon only when the application was using GPS interface. So GPS interface was only used 0.04% of the time. So more frustrating stuff. We found out that these sensitive requests happen once in every 15 seconds. So 213 times per hour, per user during the study period. So if you are to prompt the user, if you are to ask the user every single time there is a sensitive request, it's practically impossible. But what we found out from our exit survey was that 80% of the users wanted to block at least one permission request, which means they wanted that option to block it at runtime. And overall, they said 35% of the permissions were deemed inappropriate, meaning that they want to block them. So users wanted the option, but the way that third-party applications are behaving makes it impossible to give them the option. So then the first thing is to understand what are the factors that users are using to decide to allow or deny a particular permission request. So the first one is that the extent to which they expected to have the particular permission request also kind of had a significant impact towards their decision, which complies with the initial notion that I mentioned, the contextual integrity, which suggested that their privacy decisions are driven mainly by the expectation. And also, the visibility of the application requesting the permission, whether it's running invisibly to the user or running visibly to the user, also had a significant impact. So now we are in a dilemma. Users wanted the option, and now the way that the applications are behaving is not giving that option. So we wanted to try whether we could use ML techniques to learn the user's privacy preferences and start predicting their future decisions for them, so that we don't have to confront the user every single time that there's a request. So to understand that question, to explore that space, we conduct another user study, another field study. The key differences in this study from the previous one was that we broadened the set of information that we collected. Earlier, we only collected the runtime information and the contextual information. Now, we are also collecting behavioral data. We collected every single behavioral information that can be observed from the platform, like their looking behavior, like their browsing habits. And rather than probabilistically taking a screenshot, we now probabilistically prompt the user. Like this. Whenever we encountered a sensitive request, we prompt the user, hey, this application accesses your location or sensitive resource. If you had the option, what would you have done? So these responses serve as the ground truth for our ML model. So we did the study for 7 weeks, and we had 133 users using our system as the primary phone. And then during the study, we had 4,224 prompt responses and 176 million events. These are behavioral events, they are runtime events, and out of these 126, 96 million were just related to sensitive resources access. So that's an increase from previous once in every 15 seconds to once in every 6 seconds in the second study. So, and now, so we had the enormous data set, and now we want to predict their privacy preferences. So these are the 3 different feature groups that we used in our ML model. The first one is just basic permission information, like what's the type of the permission, location, Wi-Fi, and then what's the visibility of the application running, application request in the permission, and time of the day. And the user behavior. The 3 different behavioral traits came up more predictive than other groups. Their browsing habits, their audio preferences, their screen locking habits, whether they have a screen locking mechanism or not, how often they unlock it, how often they get their password incorrect. And then the most predictive group is their past decisions. How have they reacted when the application request in the permission was running invisible? For an example, what was their previous decision when the Facebook requested location when the Facebook was running invisible as a service compared to when it was running visible? And the other condition is that the foreground application, how they reacted to the prompt when they were using Facebook, or when they were using a banking application, or when they were using a game. So the intuitive behind the past decision is to understand how they capture the context, how they capture the surrounding information when they respond to the prompts. And using these prompt responses, we simulated the ask on first use, which is the status quo right now. This is the latest permission model in Android 6, and that has been there in iOS for some time. And we found out that it's only effective 80% of the time. So 1/5 of the time, ask on first use will do something different from what the user would have done if they had the option. So the 20% is a significant portion if you have sensitive privacy leaks once in every 6 seconds. And it also required 12 prompts per user during our study period. So they'll be prompted 12 times. And then we tested our ML model just using behavioral data. The error rate is slightly decreased, so it is slightly outperforming. But the significance in this observation is that this behavioral data does not need user involvement. These are all passively observed from the platform. So we don't have to prompt the user. And then we use the ML model with the full feature set, and then we reduce the error rate by 80%. So the ask on first use has an error rate of 19.47. Now our ML model has 4.27, which is a significant error reduction. But it also required more user involvement compared to ask on first use. And then we reduce the initial user involvement, and the ML model will still outperform the ask on first use even with a significantly lesser number of user involvement. So what do we learn about these observations? So as I mentioned earlier, as the notion of contextual integrity suggests, that privacy is contextual. Users do make contextual decisions. That's why the foreground application, the visibility of the application request and the permission came so much significant. And then, so if a platform wants to protect, safeguard the privacy, they have to start capturing these contextual information in the platform. And they also have to learn users' privacy preferences before doing so, because each user has unique privacy preferences. You cannot have a single model that works across all users. And we also showed that you can do that. You can learn users' privacy preferences and predict them with a very high accuracy compared to what we have right now. And then what is the passively observable behavioral data means is that with the introduction of IoT and wearables, now you have a billion different ways that they can invade your privacy. But the issue is that these things are not equipped to have active user involvement. You cannot prompt in this tiny screen. So you could use these behavioral data to learn about their privacy preferences and then start making decisions. So if you want to know more about our first study, it's published in Usenext last year, and the second study, the use of ML and the behavioral data, hopefully will be published soon. It's under submission. Yep. If you have questions, I'll be glad to answer right now, or we can take it offline.
Cooper, can I ask a question?
Yes.
You have to speak into this. Oh, sure.
Do you have stats about whether, for example, apps are asking for permissions, like detecting when the screen is off and asking and getting permissions then? So like saving their location request for when the screen is off so that the user doesn't notice the location icon?
So from the first study, we had a few 4 to 5 different applications who had a statistically significant lenient towards requesting location when the screen was off. We don't know what factors triggered them, but when we look at the numbers, they had a higher tendency of accessing location when the screen was off. So that's about it, because we don't have the app logic, we don't have access to app logic. So statistically speaking, that's.
And what about the same thing, but with like microphone permissions?
One thing that I should mention is that we only monitored 12 different permission groups. There was a study done a few years ago that said there are 12 different permissions, like accessing your browser history, accessing your call logs, accessing your SMS. So accessing microphone is not one of the things that we monitored, but it's just a matter of extending the instrumentation. But that's something that we want to do in the next study. Okay, yes, we did. That's how we actually instrumented for web browsing, because we decompiled Chrome, Firefox, and all these things. Okay, I'll take questions.
Great. Questions later. Sorry.
Hey, I am Kashmir. I'm going to put a stopwatch on to try to actually keep this to 10 minutes. I'm Kashmir Hill. I'm a reporter. I've been writing about privacy for about 10 years. And thanks very much to other presenters. I'm really excited to use the information and tools from your presentations. I already have some plans for Recon. But I'm here to talk to you about, well, what I want to know, are mostly people in the audience technologists? People just interested in privacy? Okay. My presentation is a little bit how to make the privacy invasion that you discovered go viral. Which one easy way is to send it to me. So this story starts with a professor at the University of California, Santa Barbara, who sent me a DM via Twitter. I have open DMs because I do like to get story tips from people, though I often get like crude photos and weird messages. But this one was a good one. It was from Ben Zhao, and he told me he had this paper about Waze. How many people here use Waze, the traffic app? Whoa, no one uses it?
No, there was.
Holy shit. So, no Lyft drivers in the audience. So it's much like Google Apps. It's owned by Google. It was developed by an Israeli company. It monitors traffic and tells you the best way to get around. It's actually quite a useful app. Though neighborhoods. It's out now. I'm sure it was, started by somebody who was in like the Israeli intelligence. But a lot of neighborhoods hate it because it sends people off of highways and through like shortcuts through neighborhoods. But anyways, he told me that he'd done this paper and they discovered that you could, what did he say? It's fairly easy for hackers or anyone with reasonable tech skills to spoof cars in their systems, create fake reports of congestion, traffic, more importantly, to silently and invisibly follow other Waze users 24/7 without being detected, which is the line I read that I got really excited about because that is very privacy invasive, which is something I'm always interested in. And then I actually looked at the paper, and it was a little dense. The title was Defending Against Civil Devices and Crowdsourced Mapping Services. So I had to read through this. It was very technical. And so then I had a call with Ben about it. And then I was a little worried because I went and checked this. Sorry, this is like not working super well for my presentation, but this article was from 2 years earlier, and it said, students hack Waze, send an army of traffic bots. It was published in 2014, so I was like, oh, it sounds like this story's already been done. But then I went back to Ben and talked to him, and there was a difference between the Israeli students' hack and the UC Santa Barbara team's hack. The Israeli students had used emulators to create, the Wired headline kind of blew it up a little bit to say it was an army. They basically could, put 2 or 3 cars into the app, and that was enough to create traffic jams. Because if you just had 2 or 3 cars report that there was terrible traffic, it would reroute people. And that may sound like not a big deal, but you could actually reroute particular drivers that you were interested in rerouting, especially with what Ben Zhao and his team accomplished, because they could both track cars and reroute cars. So this could be like one of those futuristic hacks where you like figure out that the guy driving the bank's money uses Waze, and then you like track them and then create a traffic jam and divert them and then rob them. So it was really kind of like an exciting.
Totally in the Italian job.
Oh, do they do that in that movie? Yeah. It's been a while. Well.
I thought you were going to say driving into a lake.
Yeah. So Ben Zhao has the way to do that. Or you could get your enemy to drive into a lake. And what they had done was something a little different. They had actually, rather than doing emulators, they were able to, Waze servers communicate with phones using an SSL, encrypted connection, except they were able to intercept that connection by getting the phone to accept their computer as a go-between. And so then they were able to reverse engineer the kind of Waze backend server language, and so then they could just write scripts that were able to talk to the Waze servers directly and basically turn it into an API so that they could pull down information and send information into it. So they were literally able to create armies of cars, and then they said they could track individual users. And they said they'd done it with one of their students. And I said, well, I really like when I do my stories for me to experience the privacy invasion if I can. And so I'm going to Vegas this weekend. I don't usually drive, so I don't usually use Waze, but I'll be in taxis a lot. So can you guys try to track me? And they said, sure. And so I told them where my hotel was. And after I was there for a day, they sent me this trace, which showed exactly where I was and the time that I was there. And this is me going just from the casinos where I like to play poker over to downtown Vegas where I had sushi dinner. So then, so I said, well, have you told Waze about this? And they said, yeah, we sent that paper to them a year ago. And they seemed concerned about it. And it actually, one thing that they had changed since then was that Waze no longer reported your location in the background, which before, and I'm sure Recon would have picked up on this, or Haystack, it was just sending location all the time if you had the app open, even if you weren't on it. So bless you. So they had changed it so that it was only sending location when you had the app open. But that's pretty effective for tracking somebody, because if you're using Waze to get around, then you have it open on your phone. So I contacted Waze about it, and that's always the hardest part of this job of doing the security reporting, is that and I'm sure every time you guys do disclosures for those security researchers in the audience, like, the companies don't like to hear about it, and they're very defensive, and they're usually like a little bit mad. So anyways, it's like my least favorite part of it is telling Google/Waze that they have this problem, and that they had known about it for a year, and they apparently hadn't fixed it. And they said, and I told them, that I had been traced myself, which is a little ethically challenging, because this was essentially a live hack of Waze's servers, where they were going in and seeing my phone, communicating with it and pulling that information out. And they could do this with anybody, but they were only doing it to people who had given them permission, so his students and me. So I contacted Waze, and when Waze said, I wrote my story, which was, if you use Waze, hackers can stalk you. And I basically just explained the hack, explained that it had been used to trace me, that I told Waze about it. And then my article kind of went very viral. A lot of other people covered it because Waze is such a popular app. So then Google did this response, or Waze did this response, saying, first, a stranger cannot search for or find your Wazer on the map and follow you. The reporter in the article gave her location and username to the research team. So they essentially said, you can only really track somebody in the app if you've told them your username. And I had told the team my username, which was Journo Cash. And I told them where I was going to start to make it easier for them to track me. They were not using my username to track me. They were just using where I was starting from. And I thought it was, pretty unreasonable ways to respond that, that this is that this was not a reasonable defense, because I don't think that just because somebody knows where I live or where I work, that they should then be able to track my movements through Waze to the other places that I go. And they said they did some things to fix it. And so I talked to Ben Zhao again and said, well, what did they do? He said, well, they no longer report your location for when you first start your trip and when you end your trip. So they're getting rid of some of the information in there. And then they obfuscated the communication that happens. And he said, but I'm pretty sure that we can probably decode that pretty quickly. And then 12 hours later, he's like, oh, we actually did. And so this was, so Waze said, this is fixed. And I asked them if they could trace me. And this was a week later when I was driving from San Francisco up to Northern California for a wedding. And so this was after Waze had fixed the app. And they were still able to do the tracking. And so I went back to Waze and I said, hey, you guys, they can still track me. And Waze had no idea how they were doing it. And they're we fixed it. And I said, well, I don't know how they're doing it either. And Waze said, well, why don't we talk to the team, to the research team? And I was like, well, that's a really good idea, and I'm not sure why you didn't do that from the beginning. But I am happy to put the two of you in touch. And so so then finally Ben Zhao had a conversation with the engineers in Israel, and they were basically how are you still doing this? We thought we fixed it. We don't have, they've taken away all usernames. The usernames no longer appear in the app. They had gotten rid of that beginning and end of the trip. They just had no idea what they were using. And it turned out that Waze had this, among all the information that they had for each user was one field that was the exact time down to the second that somebody had created their Waze account. So it was a unique identifier associated with every person's account, and it was the thing that the team had been using the whole time to do their tracking. And so finally, when they talked directly, Waze was finally made aware of this, and so they eliminated having a unique identifier with the exact second that you created an account and replaced it with a now random number. They still have the field for some reason. It must be used in some other way, and they have to have the number, but now they've made it a random one. So now Waze is actually pretty secure. And the paper this is all based on, there's now a final version of it, and they presented it in Singapore this month, I think. But anyways.
Next week.
It's next week. Are you going to that conference as well?
Recon is also there.
Okay. So anyways, if you want to meet Penzao.
Even if you randomly generate it, because I mean, you could do guesses, do things like location, my father, UID. And I'll break the web protocol, Cisco guy.
Yeah.
I can find out later.
Yeah, that's the thing. Like Ben Zhao's team felt like they'd finally gotten the app to a place where it was secure enough, and so they essentially said, like, we're done doing our research now. But I would guess that if somebody paid, more attention to this and dug into it, they could probably find out, how that random number is generated and find a way that it's traceable. But it is much more secure now than it was before, and yeah, it was an exciting story. I was so happy that that Ben reached out to me about it, and this is just sometimes necessary. Google knew about this. They had this full paper. This is like the final version, which is a little different, but this full paper had been already put online in 2015. They had sent it to Google, and just nothing had happened. So sometimes you just need a really annoying journalist to help get things fixed. And I'm always happy to be that annoying journalist. So if you ever have ideas or things you want me to go after, I'm happy to do that. Anyways, that's the Waze hack. And I guess none of you use it, but I actually do recommend the app. It's really useful if you're on road trips. Any questions?
I have a comment. I have one question.
All right. Good.
Yeah. Have you looked in at all at Facebook's practices on using your location? For instance, I went to a group counseling session with my son, and I met a bunch of people I'd never met before. And that evening, when I checked into Facebook, there was a picture of one of the people at the counseling section being suggested as somebody I ought to be a friend with.
Oh,
never met him before.
I
thought that was interesting.
I mean, Facebook is definitely using location. I've been writing mostly about their use of location for ads. So we did a story. A pro-life group has been targeting ads at people who go to abortion centers, because you can now target ads to a specific location within 150 feet. So they'll do pro-life ads at an abortion center. So if you're in the waiting room waiting to get an abortion for whatever reason, you check Facebook, you'll get an ad saying, showing photos and stuff like that. So that is happening. A senator in DC used the same targeting. It was an Alaska senator who wants to get funding to build a road to two really remote towns through protected wilderness. And so she was targeting the Department of Interior with ads trying to promote this, because they've been resisting it. So I have heard about the use of location for that. I haven't heard about the use of location for actually making friend connections. I think that would be very troubling if that's happening, so I'd love to talk to you about that. The hard thing with Facebook is that sometimes people get friend suggestions and the information flows are not super transparent. So a lot of people don't know that once you put Facebook on your phone, it automatically sucks up all of your contacts and it will recommend those people. So if there's somebody you put in your phone, 7 years ago, all of a sudden they'll start popping up as a friend. So it's just
automatically they actually have to pop up after. They actually have to get your permission.
I think you have to deny permission.
Yeah, you can deny.
Yeah, I think it used to be seamless, and maybe they have changed it since then. But it used to be just something that was in the permissions that it has access to your contacts. So yeah, I will look into that. If they are using location to make friend suggestions, that is
They also do things like when someone
surprising.
else searches for you, they show you that person.
Right. That definitely happens. But so another thing could have happened where you went to this meeting and then, you know, you were with somebody else who then friended that person on Facebook, and so then they started sort of recommending it to you. There's just like different ways it could have happened, so it's just hard to kind of track those down and find a definitive answer. I think he had a comment, unless you want to open up the floor just generally to comments.
Yeah, I just. Well, I'm gonna like. Okay, yeah. We'll break from this format, and then we'll all get to talk amongst ourselves and share all of our things. But big round of applause to all of our speakers. And big round of applause to ICSI, which gave us this wonderful space. And to the Christian Science Monitor Passcode publication, which is doing the live stream online. Thanks everyone for coming. I have to run, but if you want to send me comments or suggestions for future events, I'm noah@eff.org, and I hope you all have productive conversations until whoever decides kicks you all out at a timely time. So, but thank you all for coming.